Okay, all right. Hello, everyone. Welcome back to MLSS-Indo Lecture 2 with the topic Deep Learning Fundamentals. Again, here with us, Daniel. Um, how about you, Daniel? Is it okay to continue with only 1 hour break? Have you recharged? Okay. Thank you, Daniel. Okay. I'm not gonna take much of your time, so please start the lecture, and yeah, so we will have more time to questions later. I think yours muted. Uh, Wait, okay, yeah.
Okay, thank you. I think I need to be made a co-host again so I can share my screen. That was why I couldn't unmute myself as well. I think when I signed out, or maybe I'm in with a different account. That might be the issue. Sorry. While we're waiting for me to be made a co-host, I hope everybody had a nice, refreshing break. And this lecture is going to be not so dependent on what happened in the previous lecture. This is more sort of a background on deep learning, which is a branch of machine learning. Can I be made a co-host yet? Ah, perfect. Right. Okay, I can share my screen. Fantastic.
Sorry for that.
Oh, no worries, no worries. Right, here we are. Okay, yeah, so this lecture is going to be on deep learning fundamentals or basics. Again, not as basic as it sounds, but we're going to be covering yeah, sort of some of the techniques which you encounter again and again and again in this subdiscipline of machine learning. Now, the topics I'll cover, I'm going to look at classification as sort of a primary example, and then we're going to start off with logistic regression, which is a form of classification, and we're going to build it up into a deep neural network. And we're going to look at some of the problems which you often encounter in deep neural networks to do with gradient-based learning, the backpropagation algorithm, how to deal with vanishing and exploding gradients, so things like initialization and activation normalization, and then how a general framework, how people tend to design these deep architectures. And then I'll finish with a few examples of different kinds of network which people use in practice, which are adapted to particular domains. So, oh, if you didn't recognize this monster in the back, it's a Komodo dragon. And you can find them on the Komodo Island, which is, I think it's in Nusa Tenggara, which is sort of like east to central Indonesia. It's a super, super cool place. It's the largest lizard on Earth, I believe. Right. So what is logistic regression? So logistic regression is a classification technique. Funnily enough, it's called regression, but it is classification, and it's an example of what's called a discriminative model. A discriminative model is a model where you build a probability distribution over predictions given an input. So this is an example of what we have. We have blue points here and red points, and we want to be able to say what is a blue point or a red point, and we want to distinguish between these two. So these points will have a numerical input, so that will be the position along this x-axis, and then they'll have an output which I'm going to label as a 0 or a 1. So actually these red points here would be down on the same level, but they're sort of drawn on a different level on this y-axis just to show that they're different points, but they would actually all be in the same one-dimensional space. And logistic regression is about separating these points with a rule. So in the general case, the input space X, remember we're talking about supervised learning, you have inputs and outputs. The input is some d-dimensional vector, and the output is a number which is either 0 or 1. So this is a binary case. And you have training examples in your data set. So you have pairs of inputs X and outputs Y. So for each training point, you have both its X value and what it should be, 0 or 1. And you can associate labels with these zeros and ones. So maybe 0 would be cat and 1 would be dog, for instance. People do this kind of thing. And the model we use is a probabilistic model. We assume that there's this thing called a Bernoulli distribution, named after a mathematician called Bernoulli, which has an output distribution over y given some probability pi of x. So pi isn't the number 3.14, etc. It's now a function of x. And so let's just see, if y is equal to 1, then you have pi to the 1, which is just pi, times by something to the 0. So actually, if y is 1, then this is pi of x. And if y is 0, this term becomes 1, and this term, 1 minus pi, becomes your sort of dominant term. So this allows you to say, we select a label y with probability pi, and a label of y equals 0 with probability 1 minus pi. And interestingly, this probability here is a function of x. It's a function of input here. And we can build this function from elementary components, such as we're going to take x, we're going to pass it through a linear function. So we'll take the inner product between x and w, and then we'll pass it through this sigma thing called an activation function, or a sigmoid function, which has this form. And this sigmoid function looks like this blue curve here. And so we can expand y actually, we can expand w. Actually, I've got it written here. Normally, we can rewrite our w's and x's in such a form, or if you have one-dimensional x's, you rewrite your one-dimensional x as a vector. You write it in this form. And we can associate the parameters of this w as like a scalar w and a scalar, what's called a bias b. And w, like it modulates, it changes the slope of this sigmoid function. So bigger W gives you a steeper slope, much more sharp thing. So this sigmoid will be more sharp. Smaller will make it more shallow. And B will determine where this sigmoid is positioned along the x-axis. So by changing W, you can change the shape of this sigmoid function. So the sigmoid is between 0 and 1, so it is we've chosen it because it gives you numbers between 0 and 1, which we can use to model pi. So this is the basic formulation of logistic regression, which is this classic technique. Now, what we want to do is we want to find out, given some data set, we want to find out the likelihood of W, and we want to then maybe use some statistical technique, maybe Bayesian inference, which we looked at previously, to find a probability distribution over the W's. But that only works if you have distributions in what's called this conjugate exponential family. But although the Bernoulli is in the conjugate exponential family, when you combine it with this particular function pi of x, which is a sigmoid function, it no longer is in the exponential family. So there doesn't actually exist what we call a conjugate prior. So we can't actually do Bayesian inference very easily in this framework. So people usually resort to either taking approximations to the posterior in W given some data, or they will do this other thing called Monte Carlo sampling. Or what most people do is they just say, you know what, I'm not going to bother with that. I'm just going to do maximum likelihood. So that's what we're going to do. If you write it out, you can write out your likelihood function or your log likelihood function or the negative of it. As such, if you fill in the maths from the previous term, then we get this thing here. And if any of you have any experience with using PyTorch or TensorFlow, you will recognize this function as something called the cross entropy function or the cross entropy loss. And the cross entropy is nothing but the negative log likelihood of your parameters given your data. Okay, we want to take the maximum of this, or the minimum actually, sorry, because I put a negative in front. Maximization and minimization, by the way. I think I saw a question in the previous lecture. What's the difference? Well, there is no difference really, apart from the fact that taking the minimum of a function is the same as taking the maximum of the negative of that function. So we can always just talk about minimization, and we can turn it into a maximization by sticking a negative in front. So we can optimize this using our maximum likelihood framework by taking the minimum of this expression. And what you do is you take the derivative, you set it to 0, and you solve. This is what the function looks like in terms of that w and that b I showed you for this one-dimensional case. So when w is bigger, remember you get a sharper sigmoid function. When w is smaller, you get a flatter one. When w goes negative, the slope inverts, and b determines the shift or the offset of this function, the sigmoid function along the x-axis. And you have these isocontours here, and the minimum of the negative log likelihood is this x. And so we want to find, we basically want to find this point numerically. So what you can do is you can do some maths, you can follow this up in your own time, and then if you do that, you can get some gradients, which turn out to be the prediction error. So this is your true, so it's a negative sum of the true labels y minus, and this is that pi function from before, sigma of w transpose x n. So this is your predictive probability. And this is y minus that prediction. Y is a number which is either 0 or 1. The sigma is a number between 0 and 1. So when y is 1, we want the sigma to be close to 1. When y is 0, we want sigma to be close to 0. And so basically this says how incorrect my predictive model is. And this is what the gradient is. Then you can set this equal to 0 and you can solve in terms of w. That isn't so easy, it turns out. You cannot do this. You can't solve it on paper. You actually have to resort to a numerical optimization algorithm, which I'll explain in a bit. By the way, we're going to be using lots of matrix calculus ideas. Again, this sort of stuff is not easy. I would go and read about this in your own time. There's a good Wikipedia page, or there's this thing called the Matrix Cookbook, which is online. Essentially, we're used to doing calculus with scalar quantities, you know, df by dx, dy by dx, or whatever. But matrix calculus is basically the same thing, but when the top and the bottom half of this derivative are vector or matrix quantities. So you see the derivative of a vector y with respect to a scalar x is a column vector. Here it's something else. These things are, I think, the bane of any poor master student's life. If you're trying to do these for exams, it's I see Pat Saeed smiling here. I think he went through the same the same torture. But yeah, don't worry. Most people don't actually have to use this so much. Most of this is done under the hood in terms of deep learning nowadays. You don't have to work this out by hand. So that was binary classification. Another problem is multi-class classification. So now it's exactly the same idea, but instead of having 0 and 1 as your output, you have C different classes, 0, 1, 2, etc. up to C minus 1. And again, we can associate a label with these: cat, dog, orangutan, etc., ice cream, whatever. Maybe we have images as the X's on the left and outputs as labels. What do we do for this? It's a very, very small change. We just change the output distribution from this Bernoulli to another thing called a categorical And the categorical distribution is a distribution over C different distinct classes. And now what we do is we do a bit of an interesting switcheroo with the labels Y. We represent them as these things called one-hot vectors. So this is a C-dimensional vector with zeros everywhere apart from a 1 where we have the true class Y. So if Y1 is equal to 0, then the 0th element will be 1 using 0 indexing notation, and everything else will be a 0. And then you can write the probability distribution down in this very compact form here. It's a product, so this means the multiplication of the pi. So there's multiple pi's now for each class. And so this pi is, again, a C-dimensional vector. It sums, the elements of this pi sum up to 1. Another way of talking about this you see in notation is using this triangle thing here. So the pi is a vector in what's called the probability simplex, the C minus 1 dimensional probability simplex. This is all just fancy ways of saying that pi sums to 1. And the categorical will, if Y is this one-hot vector, this will just return the pi C corresponding to the YC equal to 1, because all of the other YCs will be 0, which will be pi to the 0 gives you a 1, and it will only be 1 for the correct class which we're interested in. This is an example of what the probability simplex looks like. If you have 3 axes, pi 0, pi 1, pi 2, then all of the vectors which sum to 1 live within this sort of triangular space spanned by these 3 points here. And the categorical vectors actually live on the tips of this triangle. In higher dimensions, you can't draw this. It will be a much more complicated generalization of a triangle. So this is the probability distribution we use. There's a lot of complicated geometry in there. Doesn't matter. In the end, it just boils down to some mathematical expressions. How do we get this pi vector here? So previously we used a sigmoid function. Now we're going to use this thing called a softmax function, which looks a bit like this. You take an input Z, or in this case, W transpose X, and then you, for each element, so for the cth element in your vector, which you feed in, there seems to be a mistake in this maths. Sorry, I'll correct this later. But anyway, you take the cth element, you take the exponential of it, and then you divide it by this thing on the bottom, which is just the sum of the exponents. So what this does is that when you take the sum over all of the elements of a softmax, the sum is equal to 1. So this gives us a valid probability vector which lives on the simplex, which sums to 1. So this takes some quantity and it turns it into a vector which elements sum to 1. And I'll fix the maths before I'll reshare the notes. Sorry about this. This should be a matrix, not a vector here, basically. Okay, if you do all of your gradients and stuff, you end up with something like before, where you have a prediction error here. We don't need to spend too much time on that. So as I said, actually, we can look at them before. You work out your gradients, and we want to set your gradients equal to 0 and solve for your parameters W for both the binary classification case and the multi-class classification case. We want to take these gradients, set this equal to 0, because that's how we do optimization. The problem is I can't do this on paper, unfortunately. No one can. It's what's called an intractable problem. So we have to resort to approximate numerical techniques, and the most famous one is gradient-based learning. Right. So this was our expression from before. Yeah, unfortunately, it's intractable. So we have to resort to this numerical scheme, which is a scheme for solving what's called convex loss functions. So a convex function is really just a fancy way for talking about any function that looks like a cup. So it looks a bit like, sometimes people will call it a smiley face. So you have this function f, you can see my cursor, and we classify it as convex if I can take any 2 points on the function, draw a line between them, and that line is always sitting above the function or maybe touching the function. But if this line ever intercepts the function, so maybe if the function sort of goes down again, it's no longer convex and these methods don't work. So convex methods are, well, the methods sometimes do work, but it's only guaranteed for convex loss functions. And it turns out that this logistic regression problem is convex. As we saw, let's go back to our loss function. Where was it? Here we are, here. It turns out that this, which is the isocontours, looking, so it's actually a two-dimensional function now. If I take any 2 points and draw a line between them, that line always sits above the function. So this is a convex problem. Right. Convex problems are nice because they have a single minimum. And this means optimization always has a single answer. So there's this technique which we're going to use, which is called gradient descent. Maybe it's easier with this diagram here. So say this is our loss function surface, and we're trying to get to this little point here. This is at the bottom of the function. What we do is we come up with some initial point, W0. There's X's in this diagram, but it's a W. And what we do is we improve upon this initial guess. So we say, oh, we think our minimum is here. Well, it's not. And what we do is we move down the function. And the way we move down the function is to move in the direction of the negative gradient. So if you look at the gradient of the loss function, it always points directly up the hill. So it will point in this direction, bottom left. So we travel in the negative direction of the gradient, and there's a scalar multiplier here, which is a small number larger than 0, which tells us the step length. It tells us how far we move from x0 to get to x1. And there's different ways to choose this. Normally, we just choose a small number, say 10 to the minus 2, 10 to the minus 3. And if we do this, provided lambda is small enough, our loss function, one step away from x0, will be smaller than it was before we started. So what we can do is we can take a small step, we can reevaluate the gradient, take another small step in the negative gradient direction. We keep on doing this iteratively, and we end up at the minimizer here. And this is sort of summarized in this passage here. You start at some initial W0, you find the negative gradient direction, you move in that direction, update your W. Do we want to stop? No, we go back to 2. The termination or stopping criterion can depend on all sorts of things. Maybe you run out of GPU time, or maybe you decided you're only going to run your experiment for 12 hours, or maybe there's some other criterion which you can come up with. And this is known to have what's called a convergence rate of a linear convergence rate. And the convergence rate is basically, it measures how quickly we go down the surface. And linear just means that we decrease the loss log linearly, actually, in time. But it follows this expression here. Okay, so this is an example with this loss function that we had before, this negative log likelihood. It's negative because we're minimizing. So minimizing the negative log likelihood is the same as maximizing the log likelihood. Again, maximization, minimization, the same, but with a sign flip. So we started here, we want to get here, we run this algorithm, and we go down like this. And if you plot the log error with iteration, which is essentially just plotting the height with time along the bottom, the height, we just follow this curve here. And this is a log plot. And this is the distance between our current height and what I know to be the real minimizer, which I pre-computed. So yeah, this is pretty good, actually. Okay. So gradient descent is what's called a first order method. There are actually faster methods out there. And one is called Newton's method. It's not used so much in deep learning, which we'll come on to in a bit, but it's good for this logistic regression example. So what you do actually is, before we were stepping in the negative gradient direction, why did we choose that? So what you can do is you can take your loss function and you can actually write your loss function at your new point W plus delta W in terms of the loss function at the old point, plus a couple of correction terms, which come from what's called a Taylor expansion, a second order Taylor expansion. So this is a way of writing this loss function as a value as this loss function in terms of the delta W's. And then you have your gradient here. And this is actually something called the Hessian. It's your second derivative. If you take the derivative with respect to delta W and set it to 0, you get this here. This term falls away. This becomes just G. This becomes delta W. Now you can solve this. It's a linear algebraic equation. Basically, you swing the G on the right-hand side and you take the inverse left multiplication of H, and you get this. And this is your optimal update under this particular scheme. And we see actually if this Hessian thing is the identity, we actually get the update modulo a lambda term for gradient descent. And this actually has very, very fast convergence properties. It's got what's called quadratic convergence. But it requires that you invert a Hessian. And usually for neural networks, that Hessian is going to be humongous. So we're not going to use this, but if you ever use logistic regression, this is something you should do. You can work out your Hessian as follows. And you see now, we plotted it before. This was steepest descent or gradient descent, which we had before. And now if I use this Hessian, I've got really, really fast convergence in terms of number of iterations. Maybe if we change this bottom axis into wall clock time, this would be a bit longer. Right. So this is kind of what's considered the gold standard in optimization for these sorts of problems. Okay, so what are we doing? We're trying to classify points into multiple classes, and we can do this by thinking in terms of what's called a decision boundary. So what is a decision boundary? A decision boundary is a point where the probability of being one class or the other is the same. So where it's the point where it switches from, oh, I'm 0.49 probability cat to 0.51 probability cat. It's around that sort of region. And if you work that out in this was our probability here, sigma of this W transpose X thing. If we write that out, the point where for a positive classification, we always want this to be larger than 0.5 in the binary classification case. Let's rearrange this equation. If you do that, you end up with this linear equation here. So whenever the W transpose X is larger than 0, we have a cat. Whenever it's less than 0, we have a dog, for instance. When it's equal to 0, we are 100% undecisive. You have to just flip a coin. It's 50-50. And if you know a bit about geometry, I studied this one in high school, but I'm not sure, people get different backgrounds. This equation is the equation for a line, but it's also in multiple dimensions a hyperplane, a big plane. So if we plot this out, then you have like a 2D space, for instance. So this is a 2D example. And then this W is a normal vector to what's called a hyperplane here. And this will be actually a 3-dimensional example with a 1D bias, it turns out. But essentially this W defines a line, and everything on this side of a line will be one class from the point of view of our classifier. Everything on the other side will be another class. But obviously there are mistakes, because in reality, maybe our decision boundary shouldn't be a straight line. So the question is, how do we get more flexible decision boundaries? And the answer is I've kind of alluded to it already. What you do is you use featureization. So you take some nonlinear function of the x's, but the question is, how do we choose how to do that? And there's a very simple thing you can do, which is to use a feature transform, and I use this phi here, phi for feature transform, which is learnable. So essentially what you do is we're going to replace, let's see, we're going to replace this x with phi of x. So now we have in our categorical, for instance, we might have a phi of x instead of x here. So this is the one change. We've gone from x to phi of x. And then phi of x would look like this. We have some nonlinear function sigma. So before this was a sigmoid, but it could actually be anything. under certain conditions. And then we have a linear transformation of X. And this W is usually called the weight, and this B is called the bias term. Bias actually has multiple meanings in machine learning, and we'll come on to that in a bit. And there happens to be this a couple of theorems called universal approximation theorems, very complicated things from the 90s, which actually say if, so this is a multi-dimensional thing. If we have enough dimensions for our phi, then actually this can approximate any function. So this decision boundary can be any shape we want it to be. If we have a feature transform which is learnable of this kind with a large enough inner dimension defined by this equation. So that's super cool. Now we can learn any function we want, anything at all. You name it, we can learn it. And so you'd think, okay, cool. This means we're done. We're done with, yeah, we've solved machine learning, or we solved supervised learning. It is called a multilayer perceptron. But one of the interesting things in recent years, and this isn't actually understood quite so much at the moment, this is still an open research question. Actually, this isn't a very easy, this doesn't work very well. And I think the answer lies in the fact that we need this W matrix to have an output dimension that is really, really, really big. Because this only holds in, yeah, when W is large enough. And so we move on to deep learning, which, you know, there are many ways to motivate this, but deep learning in some ways is a sort of logistic regression on steroids, I like to think of it. So maybe I will go on for another 5-7 minutes and then we'll take a break, or maybe this would be a good place to stop. I don't know.
Yeah, I think we can stop now.
Okay, so should we say 5 minutes and then we'll have like another short 5-minute break later as well?
Yeah, sure.
Okay, cool.
For everyone, please write your questions in the Rocket chat. I've seen some questions there, and yeah, I will read it for you. But yeah, we will save the question later.
Nice picture, by the way.
Thank you very much. Yeah, I think I spent just as much time choosing the title slide pictures as I actually spent filling in the content.
Yeah.
I kind of wanted to give this immersive experience, sort of pretend you were in Indonesia
Yeah,
and actually
sure.
get to visit.
Thank you for that. Have you ever been to Maluku, for example?
No, I haven't been to Maluku, unfortunately, but I had an uncle and an aunt who lived there for a long time. And there's a lot of Maluku people actually living in the Netherlands. There's
Living
a
in
very big,
Netherlands. Yeah,
very
I
big population.
Yeah.
Yeah. But most of the Indonesians here live in Den Haag. It's a city on the west coast. It's the place where you find the best Indonesian food, actually. I love it. So I live in Amsterdam, and sometimes I travel to Den Haag just to eat some good Indonesian food.
Yeah, I think every year they have kind of a festival, right?
Yeah, Pasar Malam.
Pasar Malam, yes, correct. Yeah, I went there once, and yeah, it was nice to meet Indonesian people there.
Yeah, I haven't been. I wanted to go last year, and then I was going to go this year, but then the lockdown happened, so they didn't hold it. So that was annoying.
Yeah.
Hopefully everything clears up by next year, in that case.
Yeah. Of course, I think, yeah, everyone's also hope so.
Yes, for sure. Oh, I'm seeing some questions. What Indonesian food do I like most? Hashtag out of topic question. I really like klepon because I have a massive sweet tooth. You don't know what klepon are, you should Google them.
Yeah, of course we know klepon. Yeah, it's a hot topic lately. Klepon, I don't know, somehow people debate about whether it is halal or not for
Really?
Muslim. Yeah, we also don't know why yeah, the topics become very hot, because I think it's already been here, I don't know, since for long, right?
Yes. Oh, very interesting.
Yeah.
I didn't know that.
Okay. Actually, this is a klepon. We have it here.
Oh, you have it here. Amazing.
Sorry, we cannot send it to you.
No, I could go around the Toko around the corner and buy some myself.
Okay.
Amazing. Okay, I think we've spent 5 minutes now. So okay, should we start again?
Yes, of course.
Okay, perfect. So now I'm thinking about food and I'm hungry. Anyway, so where were we? We were talking about this logistic regression problem, and then if we have these learnable features, so all we do is we change the x's to a function of x, then we have what's called a multilayer perceptron, and we can learn any classification function. And here's a couple of examples here. So that doesn't seem to work very well because it doesn't generalize well. What do I mean by that? Well, I mean it doesn't work well on new test points, and we'll understand that a bit later in this talk. But it turns out what works really well is if you make what's called a deep feature transform. So if you get these feature transforms and you stack them up on top of each other, so you have a phi L minus 1, all the way down to phi 1. And this circle here means composition. It means I take the output of this function phi L minus 1 and I put it into the input of phi L. And I get lots and lots of these. So I stack them up layer by layer. And we don't really know why this is the case. So this is incredible. We know how to build these things, but we don't know why they work very well, but they do. And in this lecture, you're going to see how to train this. So we're going to use gradient-based training. Unfortunately, we can't use Bayesian methods, although some people have tried to get good approximations, which work fairly well. If we just do maximum likelihood, though, we take the loss, the derivative of the loss function, which was this negative log likelihood, with respect to the parameters W of each of these functions, and then we can write it out using the chain rule as such. So this is just an application of something called the chain rule. We can expand the derivative again and again, and essentially we get an expression which gets you the parameters of your loss function with respect to the parameters, the derivative of the loss function with respect to the parameters of the nth layer, with in terms of the derivatives of each of the individual component functions. And I'll show that on another slide in a bit more detail. The sizes, so this square brackets means size of a matrix. The size of this matrix derivative is d by d if the internal dimensions are d, so it's d squared. And so the computational cost of computing this derivative will be a matrix multiplication of d by d matrices. Matrix multiplication is order d cubed, times by the number of multiplications you have to do, so L minus little l. Which means if you have to compute the gradient for each of these points, it's L squared d cubed if you work it all out, because we approximate this number as L in the worst case scenario. So this is a huge number. So there's this thing, yeah, and another question which people might have is how do we build these these features, feature functions which we stack on top of each other? Well, normally you just have a linear function followed by something called an activation function. And if you look in PyTorch or TensorFlow, activation functions all tend to have these sort of increasing shapes. The threshold function is a bit of a weird one, as is the GELU, the hard shrink. People basically tend to use this thing called a ReLU, rectified linear unit, or a soft plus or a sigmoid. Pardon me. So basically, yeah, this is how we build our functions. Okay, so going back to trying to compute these gradients, well, what you can do to make this more efficient is there's something called the backpropagation algorithm. And it says if I want to compute the gradient of my loss with respect to the parameters at layer L+1, I can write it as the gradient of the loss with respect to the output of my layer times by the gradient of the output of the layer with respect to its parameters. If I do this again for the parameters at layer L, instead of L minus L+1, it's an L, then I can write this as such. And you see these two terms are actually the gradient of L with respect to phi L. And then this here is the derivative with respect to the output of phi L with respect to W. And in computing this term, we actually have a shared term between the two. And in the language of dynamic programming, which you find in computer science, this is what we call overlapping subproblems. To compute this gradient, we actually have to compute a term which is also used for this gradient. So why don't we just compute this one term and then share it between the gradient for this and the gradient for this? And this looks what leads to the backpropagation algorithm. So we're going to relabel this term, or actually, as delta, and there'll be an L+1 on the bottom here, and we'll call it the reverse mode derivative. Another buzzword you can Wikipedia if you want to get more into this. And then essentially to compute the gradient with respect to the parameters in each layer L, what we do is we recursively compute this reverse mode derivative, or sometimes called the backpropagation error, and there's a simple rule. And we can then use this in another rule to get the individual parameters. I think this is a bit complicated, so there's a picture on the next slide, which I think will be more easy to explain. But this has computational complexity L d cubed, which is down from L squared d cubed. Unfortunately, this d cubed is still here, but there's actually ways to speed this up using GPUs, which we don't need to worry about. So this is taking us down from quadratic in the depth of our network to linear in the depth of our network, and the network being this concatenation of feature transforms. So here's an example of me writing a single logistic classification function. So now this is very shallow, but we can imagine this being much bigger in terms of what's called a computation graph. A computation graph is just a graphical layout of all of the mathematical operations that we have. So we have an input. First of all, we multiply it by some W, we add some beta. Actually, I've got these here. We add some beta or B, we put it through, I don't know, maybe like a sigmoid function or maybe a ReLU function or something. We then take the inner product between that and some small w, and then we will put this into a loss function, which takes in some y and the prediction Z4 in this case. And now we want to compute the derivatives of this loss function with respect to each of these parameters. So before we were calling these w, but actually there's other parameters as well. And the way how this works is we unroll from the top back to the input. So we can compute the gradient of w as the gradient of L with respect to this multiplication block, and then the gradient of a multiplication block with respect to w. And if you do that, you get these reverse mode derivatives, which I introduced on the last slide. So we can get this gradient. So Z4 is the output of this block here. And then we can combine this reverse mode derivative with the individual gradient with respect to the output of this block to W. And that gives us the derivative of this with respect to W, little w. We can compute the reverse mode derivative at the output of this block in terms of the output derivative here and the derivative of this entire block with respect to its input. And we get this. And we can keep on doing this. And so we see that instead of computing each derivative one at a time, we can compute them sequentially in this format. So we, first of all, we have a forward pass where we compute the output, and we have this thing called a backward pass, which is very neatly defined in things like PyTorch or TensorFlow as my model.backward, which computes all of these derivatives in this unrolled setting linearly. And this is like the game changer in neural networks. This made neural networks back in the 80s efficient to train, although some might argue you can make them more efficient. But this is basically the backbone behind all of deep learning, pretty much. Okay, so one problem with this though is if we want to compute our gradients with respect to these W's, we run this backprop algorithm, but a lot of the time our loss function is the sum of lots of small loss functions. It's the sum of loss functions defined for each input. So we can write it as a sum of gradients of loss functions if we want to find the gradient of the complete one. And what happens if n is really, really big? Say I have 1 million images, I have to compute my loss function 1 million times and all of the gradients, and then I can run a single gradient descent step. And even though it's linear in the number of training points I have, I don't want to wait for 1 million passes of data through my network before I take a single descent step. So there's this thing called stochastic gradient descent, where instead of using all of my data, I take a random, what we call mini batch. I take a random subset of all my data. So I've got all my gradients here. I take a random subset, uniformly sampled. Some people don't usually use uniform, but it should be uniform. And then I approximate my full gradient as a sum of these random gradients on individual data points. And there's an extra correction term on here so that these two things are similar. And that gives me a random gradient which on average points in the same direction as the true gradient. And so you see with my logistic regression function here, with the loss function, the red, if you can see it, was if I use all my data, but when I use random ones, I get a bit of noise as well. But it converges pretty quickly to the minimizer. And actually this noise, some people think the noise which is introduced from this random sampling actually seems to help with the training behavior of neural networks. It means you avoid small local minima, which we get because it's not a convex function in general. And it sort of helps actually with regularization, but that's not understood at this moment in time. And there's some extra conditions. Remember, we had this lambda term in the gradient descent. There have to be these extra conditions called the Robbins-Monroe conditions. If you stick to them, which is usually very easily done, then we get convergence. But that's just an advanced detail. Okay, So the problem is we've introduced this stochastic gradient, which is a very, very fast form of gradient descent. We don't have to wait 1 million forward passes. We can wait maybe 10 forward passes before doing a gradient descent step. But we now have all of this extra noise. So what do we do to get a better, less noisy version of the gradient? Well, there's this thing called momentum averaging. So what we do is we get these noisy gradients with this tilde on top for the noise. And maybe we'll take a smooth average. So this is an exponential smoother, it's called. We take a little bit of G plus a big bit of the previous estimate of G was. And provided our gradients don't change very quickly, with learning, this mu is a good estimate of the true gradient. And then we substitute mu in for our true learning update. Oh, sorry, this should be a T. This should be a T here. Sorry, this is a mistake. And this is called momentum. This is super common in all of the deep learning packages. Another thing you can do is learning rate normalization. So instead of using the average gradient, people use the average square gradient. Now, why would you do this? So you take an exponential smoothing of the square gradient, and then you divide your noisy gradient by the square root of this. Well, there are different explanations for why this is a good idea. As a lot of the time in machine learning, people come up with rules, they find that they work really well, but they don't have good explanations for why they work well. They just do. My explanation, which is also hinted at in the paper, is to do with the following. Say your gradients are really, really noisy, then your square gradient is going to be really big. And you can actually approximate the square gradient as the square of the mean gradient plus some extra noise term called the variance. You can actually work this out. It's roughly this. So your nu will be roughly this quantity here, where the mu is the average gradient. Now, if you substitute that in to this expression here, and we replace this gradient with its average, and we replace the bottom half with how I expanded that, you get this term. And this number is always less than 1. So what does this say? This says when I have very, very noisy gradients, what I want is for this bottom term to be very big, so that actually makes my learning rate really, really small. So noisy gradients gives you a small learning rate. I don't take as big steps in parameter space when I'm doing my gradient descent. When I don't have much noise, this sigma is going to be very, very small, and this nu is going to be close to the squared gradient. But because I have taken a square root, essentially what it says is that the bottom half will be close to the top half, so my learning rate will be close to 1. So you take large steps, maximally 1 for small noise. When you have lots and lots of noise, let's just reduce our learning rate because we're not so confident about what our learning landscape looks like. And then here is an example of different optimizers, which I copied from Sebastian Ruder's blog. And what he shows is in different colors. This red is stochastic gradient descent, very, very slow. You see it's moving slowly, but then there are lots of different other things. The green thing here is momentum. It's sort of really fast, but it kind of has problems here. RMS prop, which is this thing in black, seems to do very, very well. And there's a couple of other algorithms, Nesterov accelerated gradient, Adagrad, Adadelta, which are basically variations of this. The most famous paper, probably actually from the lab which I work in Amsterdam, despite it wasn't actually written in Amsterdam, but it's written by Dirk Kingma, is this algorithm called Adam, which everyone loves because it just works really well. Combines this momentum step with this learning rate normalization. And there's there's an epsilon here, which is just a small number in case this nu gets very, very small. And there's some extra steps actually, which they apply to the nu and the mu called debiasing, but they're not shown here. But essentially they combine these two things, and Adam works so well. It's amazing if you have a difficult learning problem. Okay, so that's one problem. That's stochastic gradient descent. So that's actually already a lot of deep learning covered in terms of the basics. Another thing which is super important to understand is the vanishing-exploding gradient problem. So we've got a deep neural network made of concatenations of these feature transforms. So this would be phi1, for instance. This would be phi2, and we can keep on stacking these things on top and on top and on top of each other in multiple layers. What's called a layer is up for debate. I tend to say a linear transformation plus some bias, and the nonlinearity is a single layer, but it's very it's open to interpretation, but this is what I'll stick with. Now, if you have lots and lots of layers chained all after one another, let's think about what happens to the gradients. So we're going to assume that we're going to make a huge assumption. We're going to assume that small deviations from x, so if I add a little number to x, that basically it acts like a linear network all the way through. And this is actually true if this is a sigmoid nonlinearity. It's not true for ReLUs and stuff like that. But we're going to assume that this is actually just a linear network. It's just linear matrices all stacked after each other. And if you assume that all of these weights here for each layer are normally distributed with a variance tau, that your inputs are also normally distributed with variance sigma squared, and that the various dimensions of x have zero correlation, so these are just assumptions to do the maths, then let's figure out what the variance looks like at the output of a single layer. Well, I can write the variance at the output of a layer as the variance of the input of a layer times by w. We're also dropping the b's and the sigmas just for this. If you work out the variance, there's a rule for this. We don't have to subtract a mean squared part here because we're assuming zero mean x's. If you work this out, expectation with respect to w and x, you get an expectation with respect to x and w, and essentially you can work this all out and you get some law depending on the number of elements in x. So there's going to be n elements, the input variance of our x's and the variance of the w's. So we've just taken random w's here and random inputs, and we're just looking at the variance of the output. We get this expression. So what does this say? This says if I take L layers, little L layers, and I look at the variance of the activations, so the variance of the features, L layers deep into my network, I can relate that to the variance at the input of the network times by n tau squared, because we've got an n and a tau squared. Sigma squared is this term here, to the power of L, because we've done n tau squared times by n tau squared times by n tau squared, etc., etc. And this is an exponential growth function. If L is bigger than 1, then basically this variance gets big very, very fast. If it's less than 1, the activations go to 0. So this makes learning very difficult because the activations either get very, very big very quickly in the network or very, very small the deeper you go. So this was a huge problem for years. And it wasn't until sort of early 2010s to 2011 when people were starting to really figure out how to combat this problem. And here are a couple of different ways. So Javier Glorot looked at something called initialization. And essentially, if you look at our activations, variance at layer L plus 1 in terms of layer L can be written using this form that we showed earlier. And this number L is called the fan in. You can do the same analysis, but on the gradients, and you get this sort of law. And in order for these two variances to be the same, we want n tau squared to be equal to 1. But if you do it for the gradients, there's the equation is very, very similar, but with an nl plus 1 here. So fan in is the number of dimensions of the input to a layer. Fan out is the number of dimensions of the output. And so we want these two equations to be equal to 1. So various people have come up with different laws. And it depends on the nonlinearities you use. So for a sigmoid or a tanh nonlinearity, anything which is smooth at 0, people tend to use this law. In the deep learning libraries, there will be like a tf.nn .init or something like that, or pytorch.nn.init, which you can use, and there'll be these Javier, or his surname's actually Javier Gloro, so you'll use Javier or Gloro initialization, and it basically takes, it sets this tau, it sets the distribution, of your weights when you first sample them before training from a distribution with this variance. I'm sorry if you can hear a siren. It's in the Netherlands. Every Monday at midday, they test all of the emergency sirens in the country. So if you can hear a siren, that's because they're testing one outside my window right now. But I'm not in any trouble, so don't worry. If they're going on after 2 minutes, I'm in trouble. Okay. If you have a different kind of nonlinearity, they've got different examples of these initializations. Essentially, what you do is you, when you start training, you randomly sample some W's and then you run gradient descent. And they pick the distribution which those W's come from to make sure that the activation and the gradient distributions are roughly constant throughout the network. And there are rules for how you do that. Another thing you can do to prevent exploding and vanishing gradients is to use activation normalization. This is a form of what's called data whitening. If you've come across data science, a lot of the time what they do is they take their data, they subtract the mean, and then they pass it through a linear transformation. Essentially what they do is they divide by the standard deviation of the data. And there's some stuff here. Okay, I'm not in any trouble, the sirens have finished. So you can, I think I'm going to skip this slide a bit, but essentially what you do is you get your data, you can subtract a mean of the activations, which you can measure on a mini batch, and you divide by the standard deviation, essentially. And this is another way to make sure that your activations are always the same, from the same distribution, sort of a unit Gaussian distribution, roughly. It's a bit weird though, but it just works. So these things, batch normalization, weight normalization, layer normalization, I think those are the main ones, are all very good ways to prevent the gradients or the activations from going too big or too small, because you always normalize the statistics of those activations to be round about 1 in terms of standard deviation. But you can read up on that in your own time. Another thing that people can also do is they can use skip connections. These are, again, a bit weird, but they seem to work very, very well. A skip connection is as follows. Say I have 2 layers here. What we do is we also add, at the output of these 2 layers, we can add the input from the beginning of those 2 layers. And the reason people gave for this is that essentially when you're doing backpropagation, if these both have small weight values here and here, our gradients are going to get very, very, very small when we do the backpropagation pass. Also in the forward pass, our activations here will be very small. So to prevent this from getting too small, we add the activations from the forward pass here. Also when we do the gradients can also go along this identity connection on the backward pass. Again, that might not be the actual reason why this works, but it works really well. And you find this in things called residual networks. A dense network is essentially a residual network where they have skip connections everywhere in the network between every single block. And these, again, these work really, really well. It's, again, yeah, deep learning is a bit of a magical science, I'd say. Maybe it's not a science. It's very, no one really knows exactly why these things work, but they do. And I'm sorry that I can't give you explanations, because I really would love to. But that wouldn't be entirely truthful if I could give you explanations. Okay, so how do we actually design these networks? How do I choose how many layers do I put in a network? How wide do I make the network? What nonlinearities do I use in the network? You can actually liken this. It fits into a broad area of different problems. It's like, say I've got a couple of points here and I'm doing regression like this, and I've got a cubic in red, and then I have 10 points which I've sampled. And now I fit a polynomial of order 1, which is a straight line, a quadratic, a cubic, quartic, quintic, etc., to these data points, well, if I have enough orders in my polynomial, I can fit all of my data perfectly. But a true mark of whether this works well is whether it works well on new data. So when I have test data, so maybe if I sample some data from -2 area, if I get good predictions, then this is a well-performing algorithm. And the same with the neural network. I train it on some cat and dog photos, and I show it a new dog photo or new cat photo, and I say, can we classify this? That's the same sort of idea, trying to pick new data and perform well. If you don't perform well, if you can fit your training data perfectly, but you perform very poorly on test data, that's called overfitting. And this is related to an idea called generalization error. So generalization error is the following. I have a predictor f, it outputs a certain value, and I can measure the loss function between our prediction and our true y on the true data set. And if I take the average across my true data set, that gives me an average loss, essentially. And this is just a funky bit of notation for meaning either sum or integral, common in measure theory, because essentially this could be a sum if these y's were discrete. And then supervised learning essentially boils down to, well, I want my predictor to perform well on this data, so we should just minimize this loss. It's an average loss, let's minimize it. So we're going to find the arg minimum, the smallest value, the f which makes the smallest value of this generalization error, or what's sometimes called a risk function. The problem is, though, this d star is the true data distribution, and I don't have access to that. Instead, I have a training distribution. I have examples of these images. And so we approximate this integral with a sum here, which is called the empirical risk. Now, this looks very, very similar because this is exactly the form of the negative log likelihood that we had before, where L is a negative log P of blah, blah, blah. And there's also a 1 on n in the front. So this is really nice. So maximum likelihood training, which we've been talking about, fits into this framework. But the problem with overfitting is essentially we can minimize this empirical risk, but it's not the same as minimizing the true risk. So that's where we get problems. So how can this help us? Well, what sometimes people do is they add something called a regularizer. So what we might do is we have a huge neural network, and then we'll add some sort of extra thing. So sometimes people add this thing called weight decay, where they say, we want a huge network, but we'll have small weights. Let's try that. And so they add some extra term here. And this corresponds, if it's a negative log prior, this turns out to be maximum a posterior regularization. There's other things like structural risk minimization, which I won't go into too much, which you can look up again. The Kevin Murphy book has a very good explanation of this. There's another framework, and I'm going to introduce these frameworks and I'll go back to them in a minute, called the bias variance decomposition. I'll talk about this in my next lecture a bit. Essentially, the overfitting happens because I have a training set which doesn't reflect the true data set. So what I do is, in a specific case where my loss is the mean squared error, I can take the squared error between my predictions and my true outputs, and I can expand it by introducing an extra term here. But essentially what I'm going to do is I'm going to take the expectation over different data sets, over different training data sets I could have, and you get these two terms when you write it out. One is a bias squared and one is a variance. The bias squared essentially says, how far away does my mean prediction, is my mean prediction from the true data? The variance says, every time I get a new data set, how different is my prediction from my mean prediction? So this says, how dependent is my model on the data set that I have? This term says, how stiff or how unable is my model to fit the data? And the optimal model will minimize both of these terms. You can also, this is done for a single y and a single x, so we can take another expectation, and it just turns out to give you an extra term, which is an intrinsic noise term. So this bias squared essentially is an underfitting term. It says how rigid is my model. The variance is how easy is it for my model to fit to random spurious sampling errors in my training data. And intrinsic noise is just noise which is just always there. It's just always in the training data. So you can show this for this cubic example before. I'm fitting a fourth dimensional polynomial to this data, and I do this with 1,000 different copies of the same data set with slightly different examples. And what we show is that actually, if I change, say, my prior here, so one question is, what prior do I use? If I make my prior bigger and bigger and bigger, or sorry, my sigma here, and the sigma basically is a covariance, so bigger covariance says my weight prior is flatter and flatter and flatter, and that makes my model a lot more flexible. So bigger sigmas give me more flexibility. I reduce my bias. And actually, this is exactly what we predicted. More flexible models have low bias. They can fit anything. And you also get increased variance. So very flexible models will end up fitting small spurious correlations in the data. And there's a sweet spot here. And we want to find this sweet spot. So these are models for, these are ways for designing your algorithms based on their expected performance on held out test data. But the problem is, so generalization error, we can't actually measure this because we don't have the true data set. How do we even choose a prior? That's difficult. I'll talk about that a bit in my next lecture. And bias variance trade-off, while people talk about it as being like the most important rule sometimes in machine learning, it assumes we have an infinite number of data sets, which we don't. So this is actually how people design neural networks in practice. What they do is they split their data into a training set and a held out validation set. You train your model on the training set, and then you test it on this second set. And then you keep on doing this until you run out of AWS credits, for instance, until you've trained lots and lots of models, and you pick the model which has the best validation error, and that's the model you use in the end. Very, very simple. And it tends to, you can show that it's related to these other ideas. But you train on your training set, test on your validation, and you iterate. Another way you can visualize it is if I have my training error and my validation error as a function of how long I train, we're essentially minimizing this gap. So I overfit on my training set. What I want to do is I want to minimize this error. So I choose the model with the highest validation error, but that will necessarily introduce extra bias into my model and will reduce my training set. I'll just skip these. Okay, so I've got a few minutes left, so I'm just going to wrap up with a couple of examples of extra neural modules that people sometimes use. Convolutions. So when you have image data, people tend to not use linear transformation. They use what's called a convolution, which is a special kind of linear transformation. And it has this form. You will see this. I don't want to spend too much time on this because I think Vincent Tatan's going to be talking about this. But essentially, a convolution is just it's a special kind of linear transformation where you have a restriction on the form of the linear matrix. And this makes it very, very efficient to run. But I won't go into this because Vincent's going to be talking about this. And so your neural networks, they look very different, but essentially it's the same old story, but we've just replaced the linear transformation with this thing called a convolution. There's other things you can do. There's other modules you can add. There's pooling, which is essentially like a kind of convolution, actually, but with a very special kind of convolutional kernel, which is nonlinear. But again, you are going to see this in your lab either later today or tomorrow, so I won't spend too much. I won't go into this. Another kind of neural network that people tend to use for time series data is a recurrent neural network. So this is an interesting one where the output of my network feeds back into the input of the network. And this is useful for time series. So because this has got a recurrent connection, we can unroll it in time. So we can actually get a sequence of inputs and a sequence of outputs. And we can actually sort of redraw this same module being tied across time. And these are very popular, but the problem is this will obviously lead to the gradient explosion vanishing problem. So there's actually a much more advanced thing called a long short-term memory network, which is from Jürgen Schmidhuber's group, which is a very, very complicated thing. I always forget what does what, but essentially it has this thing called it's got two states called a self state and a hidden state. This is a long-term and this is a short-term state. And it's got all these various operations in the middle. Most of these things come out of a mixture of intuition and a mixture of people just trying things and seeing what works. So I think gated recurrent units, GRUs, are now the big thing that people use. But yeah, don't ask me how all of these internals work. I think people have good intuitions, but no one really knows exactly what each of these things are doing. Andre Karpathy has a very good blog on this. And I think later on, Max is going to talk to you about graph neural networks. So a graph is essentially a very interesting object from a computer science point of view. You can use them to represent surfaces of meshes, molecular graphs, citation graphs, so when papers refer to each other, and each point in the graph is a point in a point cloud. And what we want to do is we want to learn neural networks which can operate on this data. And these nodes will be connected by connections. And we want to make sure that we build a linear transformation. So we've just been replacing this linear part here in the neural network. We can have a different form for images for recurrent time stuff. In the graph version, you just have a linear weight matrix which has zeros everywhere where you don't have connected nodes. So each element of your input vector corresponds to a different node, and then your weight matrix has different values which basically correspond to whether two nodes are connected or if they're not. So 4 and 7 aren't connected, so I can't link those two up, and the 4, 7 value in this matrix will not be, it will be gray. But essentially this is just another kind of linear transformation specifically for this kind of data, and I think Max will talk about that on whenever, I think it's Thursday. So the general framework for designing these neural networks is, one, you have to find your domain. You pick, is it images, is it time, is it a graph, whatever. You then choose modules which you stick in here based on intuition, and then you use this held out cross-validation procedure where you build the biggest network you can possibly think of to overfit on your training data, and then you start removing bits to increase the bias in your network. So you might make the layers smaller, you might make fewer layers, until your validation and your training error are roughly the same. But yeah, I wanted to give it a slight theoretical handle on it, because I know in the rest of your life and in the rest of, I think, of the practical courses, you'll get a lot of practical considerations as well. Okay. And I think, okay, I've gone over just 4 minutes, so not too bad. I've gone over a lot of the sort of motivations. So we started talking about logistic regression. And then I think really all of these extra things I talked about at the end are really not that important. I think really understanding why do we do gradient-based learning? Why do we do backpropagation? And why do we do stochastic gradient descent? Those are very important things to know. And this exploding vanishing gradient problem seems to occur again and again and again. So I think if you understood those parts to some degree, I think you've learned a lot of the fundamentals of deep learning. Things about overfitting, generalization bias, these are things you will encounter every day. So I think if you don't understand that now, definitely invest some time learning about it later. In the next lecture, I will talk about convolutions in a lot more detail. It's more of an advanced lecture, but I'll try to remove a lot of maths and put lots of pictures in it, so it'll become a lot more easy. Okay, thanks.
Okay, thank you, Daniel. I will still applause even though this is a virtual, right?
Thank you.
Okay, let's take some questions. In the last lecture, we read questions chronologically. Maybe now we try to sample questions uniformly without replacement, of course. Okay,
Of course.
let's take the first question. From Christian Simon, I think. What do you think? Does network initialization depend on the structure of the network or not?
Interesting. So there are different kinds of initialization you can do, and there are what's called data-dependent initializations. So in the kind of initialization that I showed you here, we've assumed a linear setup. We've assumed these sigmoid activations which have a linear gradient. Already there's I guess the network architecture is kind of somewhat included in the fact that I've shown you the dimensionality of the layers and I'm using a sigmoid. So it's appeared in there, but there are these data dependent initializations where people will take a mini batch of their data, they will pass it through the network and they will normalize the activations one layer at a time. So they compute the standard deviation of the activations of the layer. They then change the standard deviation of the weights to make it smaller or bigger, so that that activation variance doesn't change very much throughout the network. And in that case, that is very, very architecture dependent. What I tend to do, it's very hacky. You take the normal initialization and then you just multiply it by a small number, bigger or smaller, and you try a few different ones until your validation error goes down. Unfortunately, we're no more sophisticated than that at the moment, despite all the mathematics.
Okay, next question from Rian Adam. I've heard someone say that vanilla CNN solved the problem of vanishing or exploding gradient. Is that correct? If it's correct, then how?
Vanilla CNNs?
Vanilla CNN, yeah.
I don't think so. I mean, it depends. Like, so maybe if you have an 8-layer deep network, that is sort of okay, but we can't build them much deeper without things like batch normalization and proper initialization. So residual networks go into the hundreds of layers, and you cannot do that without batch normalization. I know that one. So I don't think that's true, but I'm happy to be proven wrong. Anyway, still choosing your initialization, choosing your, that is a form of combating vanishing exploding gradients. But I might be wrong. You never know. This field changes so quickly. I've got to be humble.
Okay, thank you. Go to the next questions from Salman Al-Farisi. What is actually the biggest mistake if the model doesn't converge? Instead of oscillating around 2 points, does the only problem is because the learning rate is too big?
Well, there's so many things that could be the case. Yes, your learning rate could be too big. General rule of thumb, start with a small learning rate and keep on increasing it until your network doesn't converge, and then step back a bit. That's a good rule of thumb. Or use a robust optimizer like the Adam optimizer, like I introduced. Why it might not converge? Maybe your data isn't normalized in the correct range. So sometimes if you work with, say, MRI data, the values of the pixels are usually 10 to the minus 5, which is very small. Images, it's between 0 and 255. Other reasons, maybe the task, maybe your network is just too small. You need a bigger network for the task. Maybe your loss function is very poor. So if you train like regression tasks a lot of the time, regression tasks are really difficult to train because the loss functions aren't very good. So unfortunately, there's no one rule. Unfortunately, it could be a whole number of different things. So you have to spend a lot of time on visualizations and diagnostics. A good thing to do, actually, is just one more thing I remembered, is to take a histogram of your gradients. And if your gradients are all very, very close to zero, then during training, then that means you're not learning anything. So take a histogram, if you get bigger gradients, something's happening. It's not backpropagation. So it's something else.
Okay, good trick. Next question from Mahmoud Dwi. What is the difference between log softmax and softmax?
Oh, did I write this somewhere? Well, the log sock.
Slide number 8, I think.
Okay. Softmax, log softmax. Okay. So log softmax is just the natural logarithm of the softmax. Where does that come from? I think in this particular case, we had our multinomial or multi-class regression problem. And then if you write it out, you've got, yeah, here we are. Our probability output, these probability vectors, are these pi things, which happen to be the softmax. Maybe that's not such an easy one to apply in just a minute, but essentially because we've got a negative log likelihood and we're taking log probabilities, the probabilities are the softmaxes. So we're going to take the gradient of the log of a softmax.
Okay. So it's not like a new activation function, right?
No, well, log softmax is also given a very specific name in deep learning called logit. Sometimes it's the inputs of the softmax, it turns out, but yeah, it gets a bit complicated. But it's not a new kind of loss function. But you could make one called a log softmax if you want. I'm not sure what use it would be though.
Next question, maybe.
Yeah, sure.
Have time. Okay, from Mamuku. You mentioned that in deep learning, people prefer gradient-based learning instead of Bayesian. Why is it so? What are the pros and cons?
Oh, this is a really, really good question. Actually, all the questions have been good so far, I should say. But this one is actually very interesting. People prefer gradient-based learning because it is comparatively easy. We can do it because of these deep learning frameworks where we can compute all of these gradients tractably. That is easy. We know how to do gradient descent. And the Bayesian stuff doesn't work so well because essentially when you compute a Bayesian posterior, you need to use Bayes' rule. And you cannot always write down the posterior using Bayes' rule in a tractable form. And it all comes down to basically the bottom half of Bayes' rule. The evidence is a huge integral, and we can't usually solve those integrals. So people come up with approximate Bayesian methods. These are called variational Bayes. There's things like variational dropout, which do this. And that's useful because it gives you uncertainty estimates, essentially over your parameters. So gradient-based learning is great because it's easy, but it will just give you a single value of the parameters. Bayesian learning is more descriptive, but it's really difficult, and we haven't got anywhere close to solving it properly yet as a problem. But if you could do it properly, then you would get uncertainty estimates on your parameters. You could then get uncertainties on your outputs of your network as well. There is another problem foundationally with the Bayesian problem, which is how do you choose a prior for your weights? That is not a simple question. I think there may be ideas, but I think it's going to be another 5-10 years, maybe even longer, although this field changes very quickly, before we actually get good priors. I think there's a lot of work where we actually are saying, let's forget about neural networks. There's certain limits of neural networks when they get lots and lots of weights, called neural tangent kernels, which are, okay, this is getting way above the course, but there are directions where we can link this to other areas where we have a lot more understanding. But yeah, this is a fantastic question which people in active research argue about every single day, and no one agrees on what's good. The Bayesians will tell you the Bayesian method's best. Practitioners will say gradient-based learning is best. It depends on who you ask.
Okay, interesting. There is a follow-up questions regarding the Bayesian. From Javier, I think. Do you think Bayesian neural network could have some useful application in the real world, as it seemed difficult to inference, right?
Yeah, so, okay, if Bayesian neural networks worked to a level where they were safe to use, for public uses, I could see a lot of uses. Say you do medical imaging, for instance. I have a medical scan and I use a neural network to scan for tumors in my scans. Sometimes you have a clinician who's looking through these scans for an hour. If we could automate that, that would be super, super useful. The Bayesian network would give you uncertainty estimates. It would say, I think there is a lump here, there's no lump there. And having that error tolerance is very important for people in real life. Also, people always talk about self-driving cars, for instance. You want to know what you are seeing and you want to know that you're confident in it. If your network says, I'm very unconfident, then you want to either tell the user, like the driver should take over the car again, or but the same as well, it doesn't have to be self-driving cars. In any system which is safety critical, being able to hand back to the user and say, I don't know what's going on, don't trust me, is very important, because the models could be overconfident in ways that could damage, it could kill people in some cases. You have to be very, very careful. These networks are being rolled out in all sorts of areas now.
Okay. We have like 2 minutes over. Can we take one?
Yeah, we started a bit late anyway, so let's.
Yeah. Okay, thank you, Daniel, for your questions about algorithm from Salman Al-Farisi. Towards the training performance, is NADAM a best choice? NADAM.
NADAM or ADAM?
Yeah, Nestor of momentum, I think.
Oh, let me just see if I've got my slides. So, yeah, okay, so it really depends. ADAM seems to work very well for a broad range of problems. Then there's this Nesterov idea as well, which also seems to work very well. Okay, so the real answer is I would always use ADAM just to make things work, because it doesn't need tuning very easily, very much. You just use 10 to the -3 for your learning rate and use the default parameters for everything else. It will work, but it won't always get you to the very, very best answer. If you really, really want to squeeze, I would use stochastic gradient descent with momentum, with a very, very finely picked learning rate. But you need to have access to a lot of GPUs, a lot of AWS credits. You can also use the Nesterov setting, which is a variation of momentum, which is shown to work very well. But yeah, I think momentum works best, but if you want something easy to use, ADAM is my personal favorite.
Yeah, I think everyone's personal favorites, right?
Yes.
Still, right. Okay.
I think that's half of all of all of Dirk Kingman's citations are from that one paper.
Yeah. He was my TA, by the way.
Oh, was he?
Yeah.
Amazing.
Okay, next question from Rian Adam. From your explanation, the second order method is better than the first order method. Then why isn't it popular?
Okay, so two reasons. Well, it is popular, but on low dimensional problems. So the thing is, we have these neural networks which are defined in maybe 1 million parameters now. So to essentially compute a Hessian which was this H term here, this H, this will be 1 million times 1 million dimensional. And now you have to invert that matrix. So that's going to be 1 million cubed operations, which is, we can't wait that long. People take approximations to the Hessian. Some people have argued actually that in stochastic gradient descent, where was it again? That this running squared estimate is approximating the Hessian. Some people have argued that. I don't think that's generally accepted, but a lot of people will agree with that. Some people won't. Again, it's a lot of theories, not very many answers, unfortunately. Well, we have lots of answers. We don't have many theories explaining the answers, weirdly. Lots of questions. So those are the main reasons. The other big reason, if you follow the work of a guy called Nicolas Leroux, who's a very big researcher on stochastic gradient methods, if you look at the theoretical convergence rate of stochastic Hessian methods, essentially the stochasticity in the noise dominates all of the advantages you get from the Hessian. So you get this very, very fast initial convergence, but then all of the noise we've introduced from these random gradients will keep on jumping about the optimum. And so the Hessian part is no longer useful. Yeah, this is, again, if we had second order methods which worked, we would use them. But the problem is they are, as I said, they're expensive. But when you can use them, always use them, is my advice. But unfortunately, neural networks are too big.
Okay, I promise this is the last question.
Okay. Okay, sure.
There are many questions. Yeah, people get really
send all the extra questions to me, and I'll write out answers.
Okay. Thank you. Okay, the last question today for your session is from Iputu Agi Karasugi. And the question is, what about regularizations? How much regularization should we put in the model? Can regularization methods hurt model performance too much in preventing overfitting?
Well, yeah. So essentially, I think it's going back to this slide about the way how you design a network with cross-validation. Essentially, you start off training for your first model, maybe try a medium to small size one to see if it works at all. And then if it does, just keep making your model bigger until you overfit on your training set. You're getting 100% performance. And then just slowly add. Now that you've done that, if you look at your validation error, it should be a lot worse than your training error. So now that's the time you start adding extra regularization, weight decay, or maybe reducing the size of layers, reducing the number of layers, adding extra kinds of normalization. There's all sorts of things you can do. And you just keep on adding that until you've got your maximum validation error. It really is this iterative process. And yes, too much regularization can damage performance. That's exactly what this whole bias variance decomposition tells you. If I have too much regularization, that's adding too much bias. It's adding too much rigidity into the model, because if there's too much regularization, then I can't fit all my data. Now, weirdly, models can both underfit and overfit at the same time. They will overfit because the model will have different values in different parts of data space. So it might overfit in one region and underfit in another. So designing the regularization techniques to not overfit and not underfit at the same time is difficult. I'll talk a bit about that tomorrow, actually. But yeah, too much regularization hurts. It's the Goldilocks principle, right? You not too hot, not too cold, but just right. Yeah, okay.
Yeah, thank you very much, Daniel, and for everyone for your questions. Very, very wonderful and thoughtful discussion for today. We will continue tomorrow with the third lecture from Daniel. So yeah, please join us again tomorrow and ask as many questions as possible. And yeah, Daniel will try to answer.
I will try to make more time for questions tomorrow, I think.
Okay, thank you. Thank you very much. Okay, that's all for these sessions, and we'll meet again in the next session, the first practical session, right? So yeah, for those actually who are at the beginner of in this area. Okay, thank you all. I'll stop here. Thank you, Daniel.
Thank you very much.
Bye, everyone.
we are channeling the company's artificial intelligence efforts into one recognizable organization, Qualcomm AI Research. Qualcomm invents breakthrough technology that transforms the way the world connects and communicates. Going beyond mobile chipsets, we're inventing AI technology that can be used across a wide range of products and industries, from mobile and automotive to smart homes and cities, ultimately changing the way people live for the better.
Machine learning has already entered every corner of the Qualcomm enterprise. I personally believe that Qualcomm is uniquely positioned to become a key player in on-device AI, which brings with it tremendous opportunities, such as increased data privacy for users, reliability of service, high speed and efficient use of bandwidth.
Today, machine learning algorithms such as deep learning use huge amounts of energy to power them. And as AI increasingly moves to low power edge devices, energy efficiency becomes all the more important.
The challenge we face in the future is about squeezing as much as computation as possible out of every joule of energy. And Qualcomm has a long history of delivering technologies that do just that.
Our mission is to push the envelope of AI and machine learning in the areas that will significantly improve everyday life. We are asking challenging questions, like how do we preserve communication privacy? Can we use deep learning to compress videos? How can we eliminate uncertainty when making life and death decisions? And how can we use this knowledge to optimize Qualcomm chips that run machine learning algorithms?
Qualcomm AI Research is an inspiring environment where researchers collaborate, innovate, and share their findings with the world through high-impact publications. But we do so much more than just writing papers. We actually build AI solutions that are used in billions of devices. In your cell phone, your smartwatch, your drone, your car, and all the other innovative technology of the future.
So if you're interested in pushing the frontiers of artificial intelligence, machine learning or deep learning, and above all, if you feel passionate about the prospect of bringing ideas to life and impacting billions of people, then Qualcomm AI Research is the place for you.
Semua hal berangkat dari sebuah awal. Begitupun kami menjadi pionir. Memutar roda penggerak bangsa dan terus melaju. Kami hadir seperti sebuah keluarga. Dan terus fokus membangun perekonomian negeri. Menjadi yang terdepan, mewujudkan mimpi-mimpi besar. Dari atas awan kami terus bergerak dan berinovasi, melihat negeri ini tumbuh dan berkembang. Inilah kami yang tak akan pernah berhenti, mengantarkan Indonesia ke puncak kejayaan. Karena dimanapun dan kapanpun, kami selalu hadir melayani dengan setulus hati.
History, most of the time, is born out of the simplest of acts, just like the birth of our story, starting with the pursuit to close the distance through voice, and make exchanging of informations at your own fingertips. And who could have known that was just the first step of our long journey? We had to jump even higher, to open new dimensions of opportunities, to explore the world. And we keep on transforming through different times, so that we can bring joy and progress for all walks of life. The world is always spinning, just like the sun. Your loyalty in us has always been our light to keep on innovating. No more simple beginnings, further and ahead. We have to keep on running, for you, for Indonesia, with the same vigor that has been driving us from the day one we began. Our 55 years selalu ada untuk Indonesia.